Welcome to Brain Vision.
Question 93 is an application question from information presented in this chapter. However, in this question, it also provides some additional information, and most specifically, an equation that is used to describe the energy of an electron confined to a one-dimensional box. The equation that is provided is the energy is going to be equal to a quantum number, n, which could be an integer, 1, 2, 3, and so forth, squared, multiplied by Planck's constant, squared, divided by 8, and in the denominator also the mass of the electron, and then the length of the box, the one-dimensional box. The length was given to us as 155 picometers. Pico means 1 times 10 to the negative 12. H is Planck's constant at 6.626, 10 to the negative 34. The mass of an electron we can look up, it's 9.109 times 10 to the negative 31. And then, as I mentioned, the length of the box is 155 pico, meaning 10 to the negative 12 meters. So all we have to do is plug in n at 1, 2, and 3 in order to calculate the energy of an electron in these quantum states, 1, 2, and 3. For the energy of the electron in this box, in the first quantum state, it has 2.51 times 10 to the negative 18 joules. You will notice with this equation, all we're going to replace is n up here, so we're going to go from 1 squared to the second energy level, 2 squared, so the energy is going to be 4 times the energy in the first energy level, or 1.00 times 10 to the negative 17 joules. And then for the last one, energy level 3, we're going to replace the 1 squared, or 1, with 3 squared, which becomes 9. So the energy in energy level 3 should be 9 times the energy in the first energy level, or (2.26 times 10 to the negative 17 joules. For the second part of the question, it wants you to calculate the wavelength associated with the energy transitions between energy level 1 to energy level 2 and energy level 2 to energy level 3. So we know the energies. The change in energy will simply be equal to the subtraction of the two energies, energy level 1 to energy level 2. And we get 7.49 times 10 to the negative 18. We then need to use the equation E is equal to hc divided by lambda in order to get the wavelength. Rearrangement of that equation is lambda is equal to hc over the energy. We just calculated the energy of the transition, so we can now calculate the wavelength of that transition. Planck's constant is 6.626, 10 to the negative 34. Speed of light, 2.9979, 10 to the 8th. And we divide by our energy, 7.49 times 10 to the negative 18, and we get 2.65 times 10 to the negative 8 meters, or 26.5 nanometers, which falls in the ultraviolet range. We'll do the same thing for the energy transition from 2 to 3. Subtract these two numbers, get 1.25 times 10 to the negative 17. Plug that into our energy equation so we can calculate lambda, and we get 1.58 times 10 to the negative 8 meters, or 15.8 nanometers, which also lies in the ultraviolet range.